Thanks, David. I hope that you've gotten the message that Excalibur is an evolving, it's an evolving system. It's designed to be dynamic. It's designed to evolve and to show us how those changes couple into the results, and to do that in a systematic, quantitative way. So we expect Excalibur to keep changing. You're an integral part of that. We're really seeking feedback from the community, and so we want you to use the portal. We want you to let us know when there's stuff that you want that you don't see, or additional data products or changes. That's really important, because we're basically prototyping the data reduction system that the CASE team is going to use for the Ariel data, and those will all be all those data products will be shared with the community as part of the CASE effort. So it's really important for you to, from our point of view, we'd really like to hear from you, and we're encouraging that. So there are a few simple ways that I wanted to go through about how you can work with the Excalibur team. So the first is, let's say that you've been to the portal and you're looking at some data, and you've got a simple question, and I'm going to call it kind of a one and done style question. It's quick. It's maybe it's like the question from the back: when do you anticipate updating the thresholds for the algorithmic classifier, for example? And that's we want to be able to answer those. So we've got a couple of ways for you to ask those kinds of questions. The first is we've got an email. So if you send an email to, where's my dot? Excalibur_help@ipac.edu. We're going to be checking that. Oh no. Oh my God. Okay. And we should update the slide on the archive. Yeah. I'm sorry. That's on me. Anyway, there is an email. You can send it to us, and we're supposed to answer it. That's the idea. The second thing is, for the next 3 months, I'm going to try hosting office hours. So we're making a commitment to the community that between 10:30 and 11 Pasadena time, there will be an Excalibur team member once a week for the next 3 months on this WebEx. So you can show up, you just walk in, ask any question you want, and we'll see how that goes. And if it's something that the community finds useful, then we'll try to figure out a way to continue it. But we're going to try that. And again, these are two good ways to express, either get an answer to a question or express, I want a something, whatever it is. I want a visualization of this, or a data product of that. Those are good ways to let us know. And, we're a small team and we do have limited resources, but we're going to try to accommodate it. And so we really want to hear from you. Okay, a second way to work with the Excalibur team is to be a collaborator. Okay, this is a little more involved, right? This is best for working together towards some sort of objective where there's going to be multiple questions as the project develops, and it's going to require a sustained period of interaction. That's great. We can support that. Collaborators are typically invited to our weekly team meetings. We run a really open team meeting. So they're collaborators are invited, and we try to support that. And if you're interested in that, then you can reach out to me, and I'm pretty sure that email is typed properly, or Heis's email. And I get a lot of email, and so if I don't respond to you, please don't think I'm ignoring you. Just send it again, or reach out to Heis. My email box is like standing under a waterfall sometimes, and so, but just be persistent. We want to hear from you, and you're going to hear from a couple of collaborators just to give you a sense of two completely different projects that are being done kind of in collaboration with the Excalibur team. One of them is from my good colleague, Lorenzo Mugnai, who wrote a paper saying my 2021 paper was all wrong. And that's fine. We want to work with, we want to work with the community, and it's fine if you're a critic of us. It's fine if you think we did the right thing. This is supposed to be a tool for the community, and it's together that we all move this field forward. So finally, the last way you can interact with the Excalibur team is maybe take the step to become a contributor. Now that's somebody who's going to develop and implement a new functionality for Excalibur. So let's say you've got a project idea and you want to process at scale across a wide number of exoplanet systems, and you want to leverage all the infrastructure that invests in Excalibur. And I'm just going to give a random example. Let's say that you want to study, I don't know, how flares interact with exoplanet atmospheres, and you want to use the entire observational base of Hubble to build synthetic flare frequency distributions for different spectral classes of stars. Okay. We don't have that capability in the pipeline. Could it be implemented based on the data that we've got going through data.calibration? Yeah, it could. So if somebody wanted to do something like that, you can reach out to us, and we can talk about how to get you involved in implementing that functionality that you need for your science program. You do need to plan on it taking a little bit of time for JPL to set up the remote access. We have done this. It took 2 months last time we did it. I don't know what the deal is, but JPL can be kind of slow at that, but we can do it and we can support that. So there's a little advantage to being a collaborator, a contributor, and that is that you have access to the entire set of data products that's in the pipeline running at JPL right now. And so I'm giving you an example. Here's what I took this snapshot a couple of weeks ago from the Excalibur portal at IPAC. And for the same planet, over here, you see the number of data products that are available that are in the development pipeline up at JPL. And so, collaborators are certainly welcome to, people who are contributing to the code base are very welcome to and encouraged to use that and leverage that in their research. All right, so I'm going to leave you with 3 takeaway messages. First of all, I want to stress, we're very supportive of dialogue with the community. We value your feedback. Exoplanets as a field has had these tremendous advances in methods and data, in the types of questions we study, in the models, and we want that feedback because we want Excalibur to reflect those advances and be a valuable tool for the community. So we solicit your feedback. We certainly hope you find the data products useful, and we'll try to prioritize your feedback in future releases. So with that, if there are no questions, we'll turn it over to, you'll hear from a couple of collaborators.
So are there any specific questions for Mark? Okay, let's give Mark a hand. Lorenzo, let's do your talk first. Lorenzo, your talk first. I should just not touch the computer. I'm not going to touch the computer. Thank you.
Thank you.
Remember the video is like
In this video. Okay.
Okay, so we're going to hear from Lorenzo Mugnai about
Yes.
okay. Excalibur versus the World, which is probably the best title of the day.
Perfect. Okay. Good morning, everybody. My name is Lorenzo Mugnai. I'm a postdoc from Cardiff University. Thank you for having me here. And this morning, I'm going to talk to you about a comparison between Excalibur and other pipelines that has been used to trend Hubble Space Telescope data with these very catchy titles. So First of all, this is just a small part of a bigger work. This is just, let's call it a little trailer of something that we are doing with the Excalibur team. So please don't share it. And most importantly, if you are curious, if you want to know more about this, you can drop me an email or be patient because we are really close to release it. So you're going to see more very soon. Now, Mark already introduced this a little. He mentioned that this collaboration started from a paper from 2021 about this planet GJ 1132b. And this paper on Astronomical Journal, it claims that it detects an atmosphere on these rocky exoplanets. On the same journal, a month later, another paper came out that I led, where we analyzed the same dataset with two different pipelines, and no atmospheric features were detected. For your convenience, I reported here the three spectra obtained with the three datasets, with the three pipelines, sorry, the same datasets. The green is from Excalibur, the black is from Heracles, and the red is for Cascade. You can see there are some differences in the spectra, and that's where we start discussing, and we decided we wanted to investigate these differences. Now, to be very honest, there are more differences because you should actually move upward the Heracles data about 200 ppm and downward Cascade has hit another 200 ppm. So there is also an offset here that should be reported. Now, before moving forward, if you want to know more about these very interesting planets, please give a read also to the paper of Jessica Libby-Roberts that was here in the Sagan workshop, or you can have a chat or give a look to the poster of Catherine Bennett that has been presented again in this Sagan workshop. She has very interesting results from James Webb Telescope. Anyway, you know everything about Excalibur now. So before moving forward, I need to introduce the other pipelines that I used. The first one is Heracles, presented in Ciara Sedor 2016. Is starts from the raw data of Hubble Space Telescope observation, and it does itself all the calibration and all the data reduction. The other pipeline is Cascade, developed by Jerome Bowman in Max Planck Institute, presented in Caron et al. 2021, but most importantly, this one starts from intermediate products of Hubble Space Telescope pipeline, the EMA products, and it uses a data-driven process to extrapolate the transmission spectrum. This ones too is completely automatic. They are both publicly available, so you can go on the internet, download them, try them, and reproduce my results. Having access to three different pipelines gave me access to three different datasets, thanks to the Excalibur portal. So here I have the three, let's call them populations that I use for this comparison work. The first one, chronologically speaking, is the blue one that is being produced by Ciara Sedol 2018 using the Heracles pipeline and includes 30 transmission spectra. Then we have Excalibur products that are 62 exoplanets produced with the Excalibur pipeline and presented in Roudier et al. 2021. And finally, I use Cascade myself to analyze and produce 22 transmission spectra using the same input parameters from Roudier et al., just for comparison reasons. As you can see, there are some intersections in these populations that we can leverage to extrapolate some information about these pipelines, so to compare them. Intersection means that the same data set has been analyzed by different pipelines. So we are starting from the same point. And we have 22 transmission spectra obtained with the three different pipelines and 8 other transmission spectra that have been obtained with both Excalibur and Heracles for the same planets. So for the first time, we can finally put all these spectra together and see if there are differences and compare them. Obviously, they are all very robust pipelines. They're all starting from the same data set. You would expect them to be pretty consistent, right? Where we can see some differences. Here we have in blue Heracles products, in green Cascade products, and in orange the Excalibur products. I classify these differences in 3 different classes. There are offsets in the spectrum. Here I highlighted some very obvious cases, but you can see there are others out there. The claimed precision can be different, meaning that the error bars are different from spectrum to spectrum, and the spectral shapes can be different. And again, some very obvious cases reported here. So now for each of these classes, I'm gonna show you just an histogram to give you an idea of what we are doing and what we are looking into. So about the offsets, I reported a ratio between the mean value of each of these spectrum compared to with the mean value obtained by Excalibur. And well, in this case, we can see that yes, there are differences, there are offsets, but there is not a big bias or a preference toward bigger or smaller radii, which is something good. About the uncertainties, I computed the ratio between the error bars in each spectral bin with the error bars produced with Excalibur. Now, these are not Gaussian distribution, of course, but it gives you an idea that averagely Excalibur produce the smallest uncertainties, while Cascade produce the biggest one. And finally, about the values inside the spectral bins, so the spectral shapes, if you want, I compute the difference between the values inside each spectral bin estimated with one pipeline and another pipeline, and I normalize it with the biggest standard deviation, the biggest uncertainties in the spectral bin. So what I would expect was an histograms centered in 0, no offset, good, with a size of around 1 sigma, because that's why I wanted the spectra to be I expected the spectra to be consistent with E1 sigma. What I actually obtain is are two histograms that are both centered around 0, good again, but the size this time is twice what we expected, which is telling us that these spectra are averagely consistent between 2 sigmas, which is still pretty good as a population point of view. This is true for every pipeline, so this is not just because I use Excalibur as a reference. If you change a reference point, you obtain exactly the same kind of histograms. So just to conclude, my easy take-home messages: difference between the resulting spectrum obtained in different pipelines, it's a real problem, a known problem in our science. I'm not the first one mentioning it. The literature is full of examples, and I'm not going to be the last one mentioning it. What I'm saying here is that we are trying to address in this problem using Excalibur as a starting point, thanks to this portal, and using the other pipelines that are published available there with the previous published population studies. So if you are curious about this and you want to know more, you can just drop me an email, because I'm very interested in the topic too. And you can just be patient, because the publication is coming out, we are soon to release it, and some very interesting results are going to be published soon. From a population perspective, back to the topic of my talk, so the comparison of Excalibur with other pipeline, we can see that there are no obvious bias with other planetary radios, which is good on a population point of view, and that the uncertainties are averagely smaller than the one obtained with other pipelines. That's basically all I had to share with you for now. Thank you very much for your time.
So are there any specific questions for Lorenzo? So I have one.
Sure.
So one of the things that Excalibur does is it goes through the data sets, and it does, this is one of the things that was talked about earlier, is that it does rejection of data that it doesn't deem that is good enough quality to do the fitting. So do the other pipelines also do that? And are you doing an actual direct comparison of the set of transits that Excalibur looked at versus those?
I'm not sure I can answer this question, because I didn't develop the pipelines. So I'm not sure. What I can tell is that some difference also can arise from the system parameters. This is another big point, probably before checking about which are the actual data that has been bring down to the final product. Which is the reason why I use Cascade also, because I had access to the input parameters too. So I had these 3 pipelines to do the comparison, but I'm not really sure about the nitty-gritty detail of each of these pipelines. So I cannot answer your question directly, sorry.
So the system parameters is the other part of my question as well.
Yeah, that's
okay.
I guess that. So I use the same system parameters used from Roudier et al. In Cascade, but of course, for the case of the Heracles dataset, I used a published dataset. So in that case, the input parameters were different.
Excellent. Okay, it'd be interesting to understand how those different pipelines use the different, especially since Excalibur goes through this data pruning process. All right, other questions? Sorry, Ellen, is there anybody online? I looked earlier and there wasn't. Okay. Oh, there's a question. I'm coming. Should have worn my watch that tracks my steps today.
Yeah, thanks for a nice talk. I have a small question about the uncertainties. So you said that the Excalibur uncertainties are to about 20% less than they are for the other pipelines. Would you say that is due to your like better reduction process, or would you say that Excalibur just underestimates the error?
That's a very good question. But again, I'm afraid I cannot answer this question because I didn't develop the Excalibur pipeline too. So I'm not sure if it's coming from the better data reduction or just a different way to estimate the final uncertainties or a binning process that might be involved with the final product or the masking procedure that have been presented this morning. What I can tell is that they appear to be a little smaller. If they are underestimated, or if they are of the other pipelines are overestimating the uncertainties, this is a full another story that we need to check by comparing the results in a different way.
Okay, I stay tuned.
Are there any more questions before I fall off the steps? All right. Well, thank you very much, Lorenzo.
Thank you.
Okay, we have one last formal presentation by Will Misener. Well, Ellen brings it up. Here's the microphone.
Cool.
And then top button is for the mouse. You have to like really hold it for a second. You have to hold it for a second before it responds.
Oh, oh.
Yeah, there's only one mouse.
Yeah.
Sorry, Ellen.
Cool.
All right. Go ahead.
Yeah, great. Yeah, well, thanks everyone for sticking around to the already into kind of towards lunch. I'm Will Misener. I'm a PhD candidate at UCLA. And just wanted to give you some context for how I've been working with the Excalibur team, kind of from a theorist perspective, hopefully not the theorists that Gael was talking about in his talk, but hopefully a nicer theorist that just wants to understand. So yeah, just a little bit of backstory for how I kind of came into this project. Right, you've seen a plot that looks something like this a couple times if you've been attending the workshop this week, right? And it's just the radius distribution of exoplanets as revealed by the Kepler survey. And it shows this kind of fascinating dichotomy. This is probably maybe the biggest result from the whole Kepler mission about how the small planets in between the size of Earth and Neptune, right? For context, this is the size of the solar system planets. So planets in between the size of Earth and Neptune are the most common planets with orbital periods less than 100 days. And they're divided into this bimodal distribution where you have the super Earths that are small and appear to have densities consistent with being rocky without extensive atmospheres. And these bigger sub-Neptunes, oh yeah, I could try to use the pointer, there it is, that have bigger radii and lower densities that are consistent with them having some sort of volatile component. And there's been a ton of theoretical work in the last 5 or so years trying to understand how this radius valley came to be. And you heard some talks about it earlier this week, including one from my advisor, Hilke Schlichting, about how a leading theory for how this radius valley came to exist is that is through atmospheric mass loss, right? That the super Earths originally looked much more like the sub-Neptunes with these hydrogen-rich atmospheres that they had created from the primordial disk, but that they somehow lost them over time through either external irradiation from their host stars, which is called photoevaporation, or from a combination of the bolometric luminosity of their stars and internal heat coming from their hot kind of magma ocean cores that keeps the atmosphere inflated and further drives mass loss. And this is called core powered mass loss. And so in 2021, I did, along with Filka, some theoretical work thinking about what actually happens as core powered mass loss goes on. And what we realized is that as core powered mass loss can never quite finish the job. And I figured, it's been a long time since any of us have had any coffee, so I'll spare you like the theoretical details, although I'm happy to chat about them if anyone's interested. But the gist of it is that as these planets lose atmospheric mass through core powered mass loss, right, what's keeping these atmospheres inflated and able to lose mass efficiently is the heat from the core. And as you lose your overlying atmosphere, it becomes easier and easier to cool that energy away. And so it actually becomes harder and harder to lose mass. And for a lot of super Earths, if core powered mass loss is the only thing that's happening to them, you could actually end up with a little bit of hydrogen afterwards, that these super Earths that look like they've lost all of their primordial hydrogen atmospheres might actually still have a little bit at the end. And so that's shown in these two figures. So we came up with this analytic scaling for how much atmosphere these planets could retain as a fraction of their total mass. And it depends exponentially on things like the core mass and the equilibrium temperature. So how big the planets are and how strong their gravity is, and how hot the heat they're exposed to is. And we found that there are pretty strong exponential dependencies on this atmospheric mass retained. And so in these figures, we showed on the left 3 planets at the same temperature but different masses. So the bigger planets retain a lot more atmosphere after core powered mass loss. And this is the same mass but 3 different temperatures, right? So the cooler you are, the more atmosphere you retain. But the upshot of this paper was that these super Earths could still have a little bit of hydrogen. And that around the same time that this paper came out, the Excalibur team led by Swain came out this really intriguing result about GJ1132b, which is a planet that falls very squarely within that kind of super Earth peak of the radius valley. And what they found is that there were these large features in the Hubble data that indicate, besides the actual species that they detect, the size of these features indicates that the molecular weight implied for these atmospheres is relatively low, that they have to have a significant portion of their atmosphere probably in hydrogen. And as Lorenzo really nicely talked about, there have been some results from other pipelines that have kind of called this result into question. There's a lot of ongoing work, which is really valuable for the field about kind of making sure we understand where these differences come from. But this result really intrigued me from a theorist side in terms of thinking about how my model could potentially explain why these planets could actually have this primordial hydrogen, because other mechanisms for mass loss or formation wouldn't really predict these low mean molecular weight super Earth atmospheres. And so that, I think at some point Mark came to visit UCLA and we had a really good conversation. And we decided that it'd be great to collaborate with the Excalibur team in understanding kind of what exactly the data says about these planets, and how we could fit my models into that understanding. So just to give you a little bit of a flavor of it, some preliminary results. This is still kind of a work in progress, but we wanted to think about things like how the initial atmospheric mass these planets could have accreted from the protoplanetary disk could affect our observations. So what is shown here are the colors are 4 different kind of plausible initial atmospheric mass fractions accreted from the disk. And this panel shows how their atmospheric mass evolves in time under core powered mass loss. And you can see kind of similar to those previous plots, how it kind of cuts off at a certain point. You end up with some residual final atmospheric mass. And how the radii evolve in time as well. And so the gray bar here indicates the actual observed radius that these planets have from the EXoplanet archive. what you're seeing here is that even though these planets lose a significant amount of mass, they're actually still a little bit too puffy to explain the observations. And so that got us thinking about maybe if you have this mass loss, which occurs very early on, and is hydrodynamic, so it kind of you lose kind of all the species in your atmosphere equally. Maybe you could have some other mechanism that increases the molecular weight of these atmospheres a little bit, enough to decrease their scale heights and decrease the radii we'd expect them to have, and could also still have lower enough mean molecular weight to be compatible with the observations. And this has been where the interaction with the team has been really valuable, right? We've kind of gone back and forth on what exactly their observations imply about things that I care about, like the mean molecular weight, and kind of how to translate things between kind of how theorists would think about it and how an observer would think about their data. So I think hopefully that's been really valuable for kind of both sides. It has been for me. And so we've been thinking about things like how if these planets then undergo long-term genes escape, if that, so genes escape is, again, I won't go into the details, but it's a mass loss process that can very strongly fractionate an atmosphere. So you lose hydrogen a lot more easily than you lose other species. And what this is actually showing is how different assumptions about this planet's actual mass can make a big difference when it comes to long-term genes escape. So these three colors are the GJ1132b planet, but modeled with the nominal mass in the exoplanet archive, and with the mass kind of larger or smaller by 1 sigma. And you can see that there are really big differences in the atmospheric mass you'd expect them to lose on kind of gigayear timescales, and on whether or not that radius that we end up with is consistent with the actual observations. And so this is still ongoing work. We have some more pieces we want to kind of fit into this puzzle. But one thing I think is really interesting from this is it's actually related to something I think Leslie Roudier said earlier in the conference, is that mass measurements, the exact masses, are really important for understanding these planets. And so you could kind of, depending on what the actual mass of GJ1132 is, if my model would kind of imply very different final atmosphere states, which I think is something that could be really interesting to look into. So I don't have any really big sweeping conclusions for you all, but hopefully this just gives you a flavor of how kind of interacting and collaborating with the Excalibur team kind of provides a lot of different avenues for new science. And so, yeah, if anyone has any questions, happy to take them.
Thank you, Will. Other questions for Will?
Yeah, I just wanted to say that my J has nothing to do with you. It's more like a reflection.
Oh, I know.
Of,
That was just a joke. Don't worry.
of my younger self.
Other questions for Will? Did you look online? I didn't see any online.
I didn't
Ellen.
see it.
So I do have a question while I'm looking
Sure.
online, which is, so this talk highlighted 1132, which is sort of
Mhm.
the one that has gotten a lot of
Yeah.
attention. But so how are you applying this to a suite? I mean, Excalibur works on a suite of
Yeah.
planets. So how are you applying your work to the suite of planets, and how does that tie in?
Yeah, we've been definitely looking at a variety of planets in the Excalibur database, kind of planets that both we sort of predicted would have hydrogen atmospheres kind of in the long run, kind of more sub-Neptune-y planets, and other planets that might have these kinds of larger features in the super Earth population. And I think that'll give us some insight into how kind of these planets evolve as a population, which is kind of always the goal with these sorts of evolution models, is kind of thinking how the whole planet population is shaped by these processes. So I think kind of, yeah, kind of in line with the goals of Excalibur, right? It's like the suite of observations can kind of inform the whole population. But yeah, I just thought this would be a good test case.
Okay. Is there a question up there? Oh, sorry. All right.